So this break from stoichiometry has been kind of nice, but we'll look at it a little bit as we check out different ways of representing an energy change for a chemical reaction. Here they're talking about something called a thermochemical equation. There are a few ways to note the energy change from a chemical reaction. Option one is that you might see something that looks like this, where at the end of a reaction, they might just say, oh, by the way, the delta H is negative 65.2 kilojoules. Or kind of like in number 9, when they're saying, hey, by the way, the delta H, the change in heat energy for this chemical reaction, is negative 561 kilojoules. When I see that the delta H is negative, I know that the reaction is exothermic, and there's an overall release in energy. Well, if energy is going to be released, you could also put it in as a product. Sometimes it might be like written in the chemical reaction, which is what we could also do in number 9. Sketch an enthalpy diagram and write a thermochemical equation. So for the equation, we could say 4 FeO plus oxygen makes 2 Fe2O3s. And since this is energy being released, it's exothermic. Energy release can be thought of as a product, 561 kilojoules. Now don't get confused with the sign. If I see delta H equals and it's negative, they're telling me that it's energy released. If we write it as part of the reaction, energy released would show up as a product. It's energy produced. Now you could also have an endothermic reaction. For an endothermic reaction, energy is absorbed. So you could see that noted as a positive delta H. Or if it's energy that must be absorbed, maybe you'll see it like this, written in as a reactant. It's energy that I have to add, overall endothermic. There's a net gain in 136 kilojoules. Oh. So 2 ways that you can see the energy term written in a reaction. Maybe they'll just put it at the end and say delta H equals. Then if it's positive, it's endothermic, energy absorbed. If delta H is negative, it's exothermic, energy released. Or they might put it in as a reactant or a product. Now, if I were to do the other part of number 9, sketch an enthalpy diagram, maybe just in general, I would draw something that looks like this. Woo! Where I'm not giving all the details. I do know that there is an endothermic component to this reaction. I'm going to have to add some energy to break the bonds on the reactant side. But if it's overall exothermic, I know that there's more energy released when the new bonds form on the product side. This negative 156, that would be like the difference between the overall energy level of the reactants and the products. So it's like this quantity of heat would be my delta H, equaling negative 561 kilojoules. That's the net energy change. Now I probably get more than that produced when the new bonds form on the product side, but I got to add a little bit of that to break the bonds on the reactant side. I have to add energy to break apart the reactants. I get all this energy produced when the bonds on the product side form. But yeah, part of it kind of cancels out that I had to add this much energy to break apart the reactants, but then I get it all back. So again, they kind of cancel, so that the overall energy change is just the difference between the reactants and the products. There should be a net release of 561 kilojoules. Now here's the part that's maybe a little bit stoichiometry-ish. What if I have a thermochemical equation, and they do have the energy term written in the balanced equation here? They've got energy on the reactant side, which is telling me that this is endothermic. There's an overall input of 136 kilojoules. Well, I want to know how much energy is required to decompose 2.24 moles of sodium hydrogen carbonate. All right, so here comes back like our stoichiometry ratios, but it's not crazy. I don't have to do limiting excess, all that stuff, but I do have to set up a proportion. All right, we can do this. So we've got this 2.24 moles. We can always start with what we're given. So I'm going to start with what I've got. I've got 2.24 moles of sodium hydrogen carbonate. Now we're going to do some stoichiometry. And we're just going to look at the balanced equation. And we're going to think of this energy value as just like another reactant. So if I look at the balanced equation, every 2 moles of sodium bicarbonate requires 136 kilojoules of energy. Well, I want to know how much energy is required to decompose just a little bit more than that, 2.24 moles. So we set up our little proportion. I want to cancel moles, and this time instead of switching it to like another reactant or another product like we did in stoichiometry, we want to switch it over to the energy value. So I can use the balanced equation to fill in that proportion. 2 moles, the ratio in the balanced equation, requires this guy, 136 kilojoules. Oh, well, yeah, I've got like a little bit more than 2 moles. So I'm going to multiply 2.24 times 136 and divide by 2. So this final answer makes sense. 136 kilojoules is required to decompose 2 moles of sodium hydrogen carbonate. I'm expecting a little bit more energy required to break apart a little bit more sodium hydrogen carbonate. The only thing that feels a little stoichiometry-like, but it's really not too bad. It's really just going to be one ratio, one proportion. Got that reaction with the iron oxide. Oh, let's see, what do we want to do here? How many kilojoules of heat are produced when 3.4 moles of iron oxide react with an excess of carbon monoxide? Which really, this, not that it changes anything, but this is right. It's Fe2O3. All right, so let's see what we got here. We start with the quantity that we're given. The number I'm given is 3.4 moles of Fe2O3. All right, so Fe2O3 reacts with excess carbon monoxide, which is fine. It's just telling me that carbon monoxide is in excess, so by process of elimination, that iron oxide must be the limiting reactant. All products formed are dependent on when the limiting reactant runs out. And one of those products is energy. With energy being on the product side, this is an exothermic reaction, and we can set up a little proportion. I want to cancel moles of this iron oxide, and I want to get over to the energy value. How many kilojoules of heat are produced? This is great now. When I say the kilojoules, I'm just going for the thermal value in the equation, 26.3. And then per mole, that's just the ratio in the balanced equation. There's only one. Oh, hey, this isn't so bad. Moles and moles will cancel, and all we got to do is plug this in our calculator, and it makes sense. So if I look at the balanced equation, every 1 mole of iron oxide reacted will produce 26.3 kilojoules of energy. Well, what if I have 3.4 moles? Then how much energy is produced? So it makes sense, we're just going to multiply, right? 3.4 moles times 26.3 kilojoules. Bingo. I get about 89.42 kilojoules released. Or maybe somebody would have written like delta H equals negative 89.42 kilojoules. When I see that the energy value is on the product side, I know that it's energy released or energy produced. It's exothermic.